Good afternoon, everyone. I'm sorry I was running a little late today. Today is our last lab, lab 13. Our previous lab 12, was skipped because that was the Veterans Day, so landed on a Thursday. So this is our last lab, Hooke's Law and bungee jumping. So Hooke's Law, we're already familiar with. We have talked about this when we do Newton's laws, when we did forces. But the simple harmonic oscillation, the second part, where you let the spring go up and down, that part was new. However, what we need to take data for, we use conservation of energy, and that's also something we have already covered. So in terms of the physics concepts in this lab, we have already done all of that. Okay, so we pretty much wrap everything before Thanksgiving. This will be our last class meeting. So next week will be Thanksgiving. There's no lab. The last week, December, Thursday in the first week of December, there will be no lab that week. So you will just do your quiz for the last class of the semester. Do you guys, before we go into the details of this lab, do you guys have any questions about anything in general about the course? I did mention that your grade distribution and grade estimate should already be in your Canvas site. If you click grades, they should show you all the scores for individual pre-labs for your worksheet. Also, at the very end of the columns, they should show you the individual breakdown of the different components, your pre-lab, your worksheet, and the quizzes, and they give you a total grade estimate. As more assignments are completed and graded, that score will be updated. Okay, so the lab final will just be the final quiz that we take on December 2nd. On the Thursday. So week 15, we do not have class meeting. You just have a final lab quiz. That's it. Any other questions about your grades? I do want to let you know that if you do want to make up some missed assignments for pre-labs or worksheet that you missed, you can still do that, and you will get partial credit for the late assignment, okay? All right, any other questions? Is the last quiz a final quiz on all the labs? The last quiz would just be focused on the last 3 labs. So we usually do one quiz per 3 labs. So it would just be like the other quiz. Okay. Any other questions? If you do think of any questions, feel free to let me know at any time. All right. Okay, so we'll get back to let's get back to our lab for today. Since you guys didn't do the previous lab 12, we will talk about the part A in a little bit more detail. So part A is calibrate your spring. Okay, so what do you mean by calibrate? Well, we want to get an idea of the spring constant of the spring. So spring constant reflect how strong your spring is. And we also get an idea of if there is friction going on in your system, we can also measure friction. So exactly this. So basically we do this by putting different weights on the spring. So the spring will be stretched by a different amount. Okay, so more weight you put on, the spring is stretched even more. So This part we did do in lab 12, but since we missed it due to the holidays, we will just make up for this part here. And we also need to use the results. So according to Hooke's law, the more the spring is stretched, the more spring force the spring provides on the object, right? So if you look at the weight, the two forces, one is gravity pointing down, one is the spring force pointing up. And the spring force is linearly proportional to how long the spring is stretched. Here is shown as the elongation of the spring, and it's called X. Okay, so spring force is K times X. In Hooke's law, Hooke's law say F equals negative KX. So the negative sign indicate the direction of the force. The direction of the spring force is always pointing up, which is opposite to the displacement of the spring. So if you drag the spring down, right, the displacement is down and the force is opposite. The force is going up. The spring will try to have a restoring force that's opposite to where you drag your spring. So in the case of static equilibrium, where the object is at rest, so mg is equal to kx. So if we add different weight and we use that as our y, and we look at the meter stick, right? We read the scale, we see how much the spring is being stretched, that's our x. So if we plot y versus x, what kind of line do you expect to get? Do you think you expect to get a straight line, or do you think you will get a curve? So if we plot here, the suspended weight is our y vertical axis and our x is elongation of the spring. What kind of graph do you think we will get? So you think it's a straight line or a curve? It's a straight line. Yes, very good. Thank you. Because the linear relationship is F is equal to Kx. That's the Hooke's law. You will also get a y-intercept. So in the perfect world where there's no friction, then you just have the Hooke's law, F equals Kx. But in reality, you have a little bit of friction going on in your spring. So you're going to have a y-intercept. So the y-intercept will tell you how big that friction is. So you get a F naught. That's the friction. So in this case, we do this measurement. We fit our data. We read a slope. Our slope will be spring constant. And we read the y-intercept. The y-intercept is our F naught. So after doing this, we consider that, okay, we calibrated our spring. We already know how the spring behaves. We know the spring constant. We know the F naught, and then we can continue to do the second part. So let's go to the first part of the data, and we'll take a quick look at the video. So here is our video. Let's come here and take a look. We'll just take a look at part A for now, okay?
Upon it the next time you go bungee jumping off a cliff.
Okay, remember we need to record our initial length and the final length, and use your use the difference between the initial and the final length to be recorded as the elongation of the spring. So when you record the initial length, it's good to pick a point that is more accurate and easier to read. So I would recommend picking the bottom of the little hook here to read, because that is not like part of the springs getting stretched. That part is solid, and also it's at the bottom, so it's easier to read. So for example, you might record the initial length of the spring is at 165.6 or 0.7. Okay, depending on who is reading it. I might read 1.165.6 centimeters to be the initial length. So let's take a look at when you add 100, start with 150 grams of mass. So that's 0.15 kilograms. And this is how the final length of your spring. So you can see that because of the meter stick is sort of put instead of from top down, the scale go up. It's kind of put in the way that is bottom up. So you can see that the scale actually reads less and less. So in this case, you just use your initial length to minus the final length. Okay. So remember what our initial length was. That was on 165.6. Here, when you add 150 grams and take a look at the bottom of the hook, where is it? It's roughly at 154.8. 154.8. So you will record on your data sheet the elongation to be 165.6 minus 154.8, and that will be your elongation for this particular data set. As you add more and more mass, the next data set, your final distance is changed now. This is roughly at 149 centimeters, right? So your elongation will be 165.6 minus 149 centimeters. So so on and so on until you have all your data. Okay, so this is part A. Okay, let's look at part B. What we do in part A is really just measure the spring, get these constants so we can use them in our next part. The second part is a spring jump. And part B and C, the physics what we're doing is the same. The only difference is part B, we use a spring, and part C, we use a bungee cord. Okay, so we want to do this. We wanted to, okay, attach a weight to the spring and let it go. First, the spring is relaxed, and then you let it go, and it will drop down to the lowest point. So imagine what it would be like a bungee jump, right? It's the bungee cord will get stretched, and it would go to the lowest point, and it will start oscillating back and forth. What we are concerned is, what is the lowest point? How much that the spring will be stretched total. Now that you can use that to help predict whether a bungee jump is safe, right? Because you want to see what's the lowest point. You don't want the lowest point to be hitting any surface, right? So we want to calculate distance d. We're going to calculate the distance t using a theoretical method, using conservation of energy, and then we also going to measure the distance d in the lab, so we record a experimental method. And then we can compare what we calculated theoretically with what we measured experimentally. Let's first take a look at how we calculate d using the theoretical method. We use a conservation of energy approach. So here our system, meaning that what objects we're interested in. We're interested in the spring and the object. Now, if you do want to talk about gravitational potential energy, knowing that Earth is also part of your system in order for that system to have potential energy, gravitational potential energy. Okay, so the system is at this location to begin with. It does not have any potential energy, elastic potential energy, because the spring is not stretched. It does not have kinetic energy because it has no velocity. So the only energy the system had to begin with was gravitational potential energy. So if we set the reference point for zero gravitational potential energy to be wherever your lowest point is. So at the initial point, you can see I'm at distance d above that reference point. So my energy is mgh, right? As you recall, that's the formula. So in this case is mg times the height, which is d. So that's my initial energy, and my final energy is purely elastic potential energy that's stored in the spring, because in this case, the spring is fully stretched. And again, you don't have any kinetic energy because your object is not moving, right? It has reached the lowest point and it cannot go down any further. And also it is at a lowest point. I've set the potential energy, gravitational potential energy, to be 0. So basically, this is a conservation of energy where potential energy has transformed into elastic potential energy of the spring. How do we calculate potential energy stored in the spring? Well, we know that you can calculate that using the work done of the spring. So the work is force times displacement, and the force is the force we got in our calibration process, right? Is kx plus f naught. So you can use that formula and calculate your final energy. All right, so that is still kind of abstract. Let's take a look at our pre-lab so we have a better idea how to do this calculation. Okay, so let's go to our pre-lab. 1 second. All right, so in the actual calculation is just like this pre-lab. So let's see how we're going to do it. All right, so what we said initial energy is mgd, final energy is this, and okay, let's expand upon that. The final energy is the integration from 0 to d, right? Because how much is the spring stretch? From 0 point to the maximum stretch is d, kx plus f naught, that is the force. Okay, so final energy, we look at the work done by spring force to calculate it, and the work is force dot into displacement, right? So f, the integral of f dx. So that's why this equation and where it's coming from. Okay, so you know, to do integral, this becomes 1/2 kx squared, the limits from 0 to d, and the integral of this constant becomes f times x from 0 to d. So that becomes 1/2 k d squared plus f naught d. So that's our final energy. And then we will use conservation of energy approach to solve for this distance d. So all of the potential energy has gravitational potential energy transformed into the elastic potential energy. Okay, so your initial energy is equal to your final energy. There is no energy transfer. So it's really just the spring going down by itself. There's no other external forces acting on it. You're not dragging it. We ignore air resistance. So there's really no energy transfer. Okay, so your total energy in the system should remain constant. So setting these two equations to equal to each other, you have mgd, which is your initial energy, is equal to 1/2 kd squared plus f naught d. And you can see from here, you can calculate d. First, let's cancel one of the d. So you end up with 1/2 kd is equal to mg minus f naught. So I found the distance calculated using a theoretical method is this. Okay, so in your lab, you should have measured k from the slope in part A, okay? And you should measure F naught, which is your y-intercept from your part A. So you could plug in your numbers for slope and your y-intercept, okay? And the weight that you added, it's already also given. So the weight that you added is this, is this much, okay? So you can plug in. So what did we just calculate? We calculate this is 2 mg minus F naught divided by K. Okay, so this is 4.41 newtons. This is read from part A. This will be given from part A. And you can calculate your theoretical value for distance d. Okay, so that's the theoretical method. Next, before we look at our experimental method, are there any questions about how to calculate d using the conservation of energy approach? Are there any questions? All good? Okay, so now let's look at theoretical method. Well, that is actually quite easy. You simply put the weight here and you let it go, and it's going to drop down to the lowest point, and you record the initial position and the final position of the spring. Okay, so let's take a look at our video for part B, which is here. All right, so let's go to part B. All right, so it will give you 3 different trials. You will record the 3 different final positions, so you get the distance d 3 different times, and you take the average to be the total, to be the experimental method for d. So here you do have to pause your video, so in order for you to be able to read the lowest point on the scale. So when you're recording data for trial 1, you can just focus on trial 1, pause it, and then go back and pause it again when you read trial 2. These 2 are listed together on your screen, but you need to take the data one by one. Okay. All right, so you may not be able to pause it exactly where the lowest point is. Feel free to do this a few different times until you're satisfied with your result. So you can see right now, I paused it so that I believe this is the lowest point for my trial 1, but it's already past the lowest point for my trial 2. So I have to go back and replay it when I take data for trial 2. Okay, so your final position, trial 1, your final position, the lowest point of the spring is around 53, okay, maybe a couple of centimeters millimeters higher. So what you could do when you do take the data, you could take a ruler and then kind of place it parallelly on your screen so that you can read the value a little bit more accurately. So let's say your final position is at 53.2 centimeters. So that's in your trial 1. You can see my trial 2 is I've already way past my my position for trial 2, but I could go back and record the data again. So here you can see it's close to the lowest point for my trial 2, which is maybe 52.8, something like that for trial 2. But you will have to take data yourself and take all 3 different data points. Okay, so they will show trial 3 later, and you will take the average of all of this, and that would be your experimental value for the drop, the bungee drop. Okay, let's go back and we'll continue with the last part of this data collection. So noticing that you are still using the same spring all throughout, that's why they didn't show you a initial position, because the initial position was already taken at the calibration process. Your initial position was the 165 centimeters. That was our initial position. Okay, so you just read data for the final. The initial is already taken down in part A. Okay, and again, you will use the difference between your initial and final position to give you the elongation, the distance of the fall. Last part, part C, we use a bungee cord. Okay, so the first part is very similar to part A, is as we gradually increase the weight, we read how much the bungee cord is being stretched. So we will measure the elongation of the cord as a function. As that increase, our weight increase as the X increase. So we'll plot weight versus X. Remember, if we were using, when we were using a spring earlier, this was a straight line. This is a linear process. But as you will discover for the bungee cord, the weight and the elongation is not linear. You check the linearity when you have your data, but you realize, no, they do not fit into a straight line. Okay, so the data collection process is very similar. Okay, so we're not gonna do that. Just take a look at that part. There's no need. I do want to talk about how to plot it. Okay, so when you put your data on the graph, you will check if it's also a linear process, just like a spring, and you realize it is not. Okay, so how do we fit the curve? If you were, I would recommend to do this using a computer, even though you do have the option to do it by hand and the graph paper is attached in your worksheet. But doing it by hand is very difficult. It's less accurate, and I recommend we'll just use our computer to do the plot. So how do you fit a curve? So if it were linear, you would have chosen the linear fit, right, in Excel. But here you would use a option for polynomial fit and choose the order to be 6. And it's going to fit the data and it's going to show an equation for you. And this function, we do need this function because we will need for the last little part of the data process. If you were to do this by hand, simply draw a smooth curve connecting all the smooth line to connect all the data points, if that's what you want to do. Okay. So after you check linearity, that is not a linear relationship. The last part of the state of this lab is to do the same bungee jump, bungee drop, and to find the distance of the fall. Instead of using the spring, we're now using a bungee cord. The actual worksheet will only require to check the distance D using a experimental method. I will talk about how to do the theoretical method soon, but that part will be an extra credit, will be a bonus point because it's a little more complicated, but it's not required. You can only do the experimental method and be done with it. And if you do more, you'll get a bonus point. So to get the experimental method, this is just the same as before. Let's go take a look at briefly take a look at our data part C, where you have a bungee cord, right? They start giving you the initial length. And then as you add more and more weight on it, you can see that the final length is different. And this is where you check your linear relationship. You realize it is not a linear relationship. And eventually you will do the bungee drop. So again, you have 3 different data trials. This is trial 1. You pause it when it's at the lowest point. You may need to do this a few times to make sure it is indeed the lowest point, and try to read the final position. Initial position was already recorded previously. Okay, this was actually quite hard to read. I think this is 110. I couldn't quite read this. So you can see, okay, so that was not even the highest point, the lowest point. The lowest point is now around 110. You may need to trial and error a few times until you are satisfied with your data. All right, so use the final position and initial position and subtract them. You get your distance d for the fall from the experimental method. So this is your experimental value. Okay. All right. So next we will talk about how to find D for a bungee cord using a theoretical method, but that part is a bonus point. Before we move on, are there any questions so far about this lab up until this point? Okay, so there's a question for part B. The initial position is the same as part 1. That's correct. Yes, part B, we used the same spring. So we calibrated first in part A, and then we let it drop in part B. So yes, the initial position for part B is the same as part 1, part A. Any other questions? Okay, now let's talk about the last bit. We'll find this D using a theoretical method, and we can compare it with what we found experimentally. This will be extra credit. Okay. Now, the previous part in part B, when the relationship is linear, that was easy. Recall what we did. We said the initial drop was mgd. That initial position was that. Final position was the integration of this force. This force is a linear relationship, right? dx. So we can easily integrate this. However, for a bungee cord, this force is not linear, as we data show that is a curve. So how are we going to integrate that complicated curve? Okay, well, so in Excel, you got this, you have just found this curve, right? And they will give you an expression. Now, your data shouldn't be exactly like mine because you need to take the data yourself. So the function you get will be slightly different from this, okay? But we can take this function, okay? And we want to be able to find the integral that represent the final energy. So this is the energy stored in the spring. Okay. Well, energy stored in the spring is really just area under the curve, right? That integration of the force dx is really just the area under the curve. So if you were to draw this by hand, you can count how many little grid is under the curve, the number of the grids, and multiply that number by the area of each of the grids. Sometimes you have 2 of the half grid, you count it roughly as 1 grid. It is doable, but it will be very hard. So I don't recommend if you do it by hand. You can if you want. Let's just use our computer to help us to find this area under the curve. We need an integral. So once we get our data, right? We can eyeball this. We can write down what the integration of this function is, and then we can enter into Excel and let Excel calculate for each of this data point what is the integration. I will show you a little bit later. But first of all, okay, for example, right now, my data reads, the first part reads negative 556,890x to the power of 6. So I know the integration of that is negative 556,890 times 1/7, right? Because this is power is 6 times x to the power of 7. Then insert your integration limit. Okay, from 0 to whichever that data point, whatever x is for that data point. And you do the same for the rest of this. So that will give you a new line. That new curve is a curve for your potential energy that's stored in your bungee cord. So here you see I have a new curve. This is my new curve. This new curve is energy stored in the bungee cord. Okay, you were wondering, okay, what do? We were saying setting initial energy equal to final energy. Initial energy is a function mgd. Final energy we have just plotted as a new curve that is also a function of d. We need to set them into equal. So another way to set something into equal is to draw both graphs on the same picture, both of the curve on the same picture, and where they meet is when they are equal. Okay, so you can plot mgd on your graph, which was easy because mg is 8.33 newtons. That was given. That's how much weight you added. And that's a straight line. And you got your new curve previously, and where they meet exactly, you can see that is your distance d of the drop, somewhere around 2 to 5 roughly. Now you will get different, everybody will get slightly different values. Okay, all right, so let's take a look at the actual process. I'm going to show you the Excel and show you how to do this. All right, let's go to Excel. So in Excel, okay, so you either have recorded your initial and final length here, or you could have do it in your scratch paper and then transfer your data points over. It's all okay. So for example, my initial length is 127 centimeters. Now when you read it, it will be slightly different. The final length is for different mass that I added. You can see the mass are in grams: 25, 250 grams, 450, 650, all the way to 1,650. So at each of the grams, you read a different final position, right? And you subtract these to get how much it's being stretched. You convert that to meters, okay? Convert that to meters. And the mass, you convert that to newtons by changing the mass to kilograms and multiply that by 9.8. That is your weight. So what are you plotting? You're plotting the stretch, that's your x value, versus your weight, that is your y value. So you're going to plot this. Remember, you need to add a 0, 0 point, which means when it's stretched at 0 weight, when you don't add any weight, it's not going to stretch at all. Of course, that should be the case, right? But we don't need to take the data point for that one. So that 0, 0 point, you just need to add it yourself. And you need to include that point in your data, otherwise your graph will be off. Okay, so you highlight these two and you will insert a chart, okay? Insert a chart for a scatter plot, and that's your graph. You wanted to add the trend line on it. As we said before, you're going to fit it using a polynomial with 6 orders. I think I may have forgot one of the data points. Okay, so now it looks a little bit better. Okay, and you also want to make the equation to show up, so they will show the equation for you, so you'll get this final data point. Okay, now you check for linearity, you realize this is not a line, this is a curve. Okay, the theoretical part for D, you will have to do it here because we want Excel to do the integration for you. Okay, so let's take a look at this function. You are now taking the integral of that function to get the potential energy, right? Because this is a force, and you need to integrate the force and distance to get the potential energy stored in the spring. So I will eyeball this equation and enter the function into my Excel. Now, for example, at this particular stretch, what is the area under the curve? The area under the curve is going to be negative. Look at this function, 63,007. Oh, sorry, is 637,626, and x to the power of 6. So I integrate that will be 1/7, right? Times the x to the power of 7. And x at that point took on this value. So I'm just going to use C22. That is my cell number to the power of 7. Okay, the next thing is the same. Next is x to the power of 5. So integrated, you will get a 1/6 to the power of 6. Again, the same data point for your x, right? And you do the same, all of this until you are done. So this is your function. You'll get, this is basically your area under the curve, and you can drag it down to fill in the data for you for all the area under the curve. So here you get a new curve. You can see this blue line is my new curve, okay? And the orange line is simply the gravitational potential energy. That's mgx. Mg is 8.33 newtons, so it's 8.33 times whatever your x was. So enter that and drag it down for all of the x's. So what you wanted to plot here, you want to plot two graphs all together on the same graph. Okay, so if you highlight all three columns and plot, they will give you the two graphs together. You fit one of them, okay, so this will be your new curve. That new curve is just an order of 2. That's good fit. And this is the straight line, okay. That was a straight line. You simply add a line fit. And then there you go. You have both of the functions plotted on the same graph, and look at where they overlap. And they will tell you roughly where the D is. You can see it's roughly between 0.2 and 0.25. It's halfway between that. So you will be able to find the D. I can change my scale a little bit so I can read these finer scale. Maximum. Okay, that might be too much. Okay, so you can change the scale so that allow you to read it a little bit better. So you can see that is actually maybe like 0.23 is where the data should be. Okay, so that is the data I took. Your data will be a little bit different. So this is how you get your theoretical value for D. As I said, this part is quite complicated. So if you want to do this, this will be given as your extra bonus credit. If you don't want, you can just stop at the experimental value. So that's part C for the bungee cord. That's all. That's all we have for today. Do you still have any questions about this lab? Any questions? Okay. All right, sounds good, everyone. This is our final lab. I appreciate that for those of you who stayed with us all the way through the semester and come to meet online every week. I had a lot of fun taking data collection together with you and teaching this course. Now, I do want to encourage you to fill in the course evaluation. Right now, we have a very low response rate, only 4%. So I encourage you to go ahead and fill in the student evaluations for the class. If you do have any questions from now until the finals week about your lab, about your grades, about anything, just email me and let me know. All right, make sure that to do your final lab quiz at the end of our last week. No class next week, and the last week you'll have one more quiz. All right, I will send out reminders on that day. All right, bye everyone. Have a good rest of your semester and best wishes in all the courses with the finals coming up. Okay, bye everyone, and thank you.